So now let's move to one of the most important developments in the history of physics. And this is how Maxwell was able to show that the four equations, which I've written here, known as Maxwell's equations in honor of Maxwell. So look at all these scientists. There's Gauss, one of the greatest scientists ever. There's Faraday. He's got things named after him too. And there's Ampere. He's got the units of current named after him. So these are all very hard-hitting, big league scientists. Well, first Maxwell corrected Ampere's law, which was wrong, by adding this displacement current term. And then he did something that was so famous that all these four laws were named Maxwell's equations. So that's how great what he did I'm about to describe. So first of all, he said, let's go to vacuum, outer space, deep outer space. There's no charge, there's no current densities. How do these laws look? Well, Gauss's electric law has got nothing on the right side. Gauss's magnetic law has nothing on the right side anyway, because magnetic monopoles don't exist. So you don't need to do anything special for that. Now, Faraday's law is always true, and it always looks like that, so you don't have to do anything to Faraday. Maxwell's modification of Ampere's law has to be used to get something non-zero on the right side for the regular Ampere's law. So this is the situation. Now, in one of the fact sheets, I show you how these four applied to suitable curves and surfaces can lead to electromagnetic waves. I'm not going to go through that derivation here. So Maxwell put these four equations together, and what Maxwell did was he used the differential versions of these. And that's how it's done in most advanced courses, not this integral form. However, you can work with the integral forms, as I have done in one of those fact sheets. You have to go and look at that as a companion to this video. But the differential versions are what are used in higher level electromagnetic theory, mimicking what Maxwell himself did. And when you do that, you end up showing that the electric field E is actually a function of both x and time, and the magnetic field B is a function of both x and time, and both of these satisfy what's called the wave equation. I want to focus a little bit on the wave equation because I know that some of our treatment of the wave equation was pretty rushed last semester in UP1. So I just want to focus on that. Wave equation is a very important equation in mathematical physics. It is any equation that can be written in the following form. Suppose I have y as a function of x and t. This could describe the motion of a wave, like an ocean wave. Okay, so the y here refers to the height of the wave. Now, as you go from point to point on the ocean, you're going to have different kinds of waves. For example, close to the shore, the wave is going to be a very big wave. Far from the shore, the wave is hardly going to be anything because the ocean is so deep there. So it changes from place to place. It also changes from time to time because as you wait, you get a big wave coming towards you. So it's a function of both x and time. Now, a wave equation is anything that satisfies the following partial differential equation. So it's the rate of change of the acceleration of the wave in this way. Del 2y over del t squared is going to be the speed of the wave squared times del 2y over del x squared. Now this makes dimensional sense because on the left side I have y, let's say it's measured in meters. So I have meters per second squared here, and on the right side I have velocity, which is meters per second. When I square it, I get meters squared per second squared, and then here I have meters over meters squared. So I have the meters squared cancelling out, and the left side is meters over second squared, the right side is also meters over second squared. Anything that satisfies this is known as a wave equation. Now, a very famous mathematical physicist known as D'Alembert, you spell his name as D'Alembert, but you write it like this. So D'Alembert showed that solutions to the wave equation are of the form y of x comma t is any function of x plus vt or any function g of x minus vt. So he's had two kinds of solutions. One is the ones with x plus vt and the other is x minus vt. The interesting thing is the combination. These combinations are, this is for the forward moving wave with a minus sign, and the plus sign is with the backward moving wave. Let's understand why the minus sign is forward moving. It's very simple. It's based on the understanding that time always runs forward. As far as we know, in our slice of the universe, time always runs forward. So if time is running forward, then in order to get the same value of x at a later time, you would need to advance the wave to the right, because v times t is a negative quantity and x minus v times t is a smaller value than just x. So you have to move to the right to get a bigger value of x to compensate for that. Likewise, if t increases, then v times t is positive, and to get the same value of f of x, of f of something, I have to make x smaller. So that's why it's backward moving, because if you make x smaller, it moves backward in the next direction. By the way, this is a one-dimensional wave equation. The three-dimensional wave equation has got one equation for x, one equation for y, and one equation for z. If it's got an equation for x, y, and z, then I would not call this y of x comma t. I'll call it u of x comma t or something, because x, y, and t are now space variables. But in the one-dimensional case, you will just have this. And we are going to stick, for simplicity, to one dimensions in this course. So the one-dimensional wave equation for, so any function, this is very general. You can write some scary stuff. So for example, f of x plus x minus x plus vt, I could write something like this: e to the negative x plus vt squared times sine of 2 of x plus vt divided by, I don't know, tan hyperbolic squared x plus vt times natural log of x plus vt. I can make anything up. I can keep writing stuff all day long and it'll be a solution of that equation. Okay, so it does not have to be anything nice looking. Now, of course, we don't want to live like this. This will be a very difficult situation. So we'll stick to what are called sinusoidal solutions. Sinusoidal are nice little things, like that be waves in an ocean. And you may wonder, well, that's a huge restriction. Look at this thing, and look at sine and cosine. They have almost nothing in common. Well, here's where the genius of another great man comes in, and that is Jean-Baptiste Fourier. So Fourier actually showed that anything like this can be written as an infinite sum of sines and cosines. Well, there goes our last remaining excuse to use something like this. We're going to use only sines and cosines because we are blessed by the great theory of Fourier, known as Fourier analysis. And mathematicians spend their whole lives working on the subject of Fourier analysis sometimes. Hard analysts work on Fourier analysis for their whole lives, and still there's so much to understand in that subject. So very, very momentous mathematical structures are being described right now. But we're going to be using in UP1 or UP2 very simple things. So I'm going to be writing the electric field as a function of x and t to be some amplitude E naught, sine or cosine, let's say cosine, kx minus omega t plus some phase factor phi. The phase factor phi takes care of all the initial condition things. Now what is k and what is omega? They're all related to v. So k is called the wave number, and it's related to the wavelength by 2 pi by lambda. Now in UP1 last semester, we introduced these things. So if you freeze the wave, there are two things you can do with this wave to make it more readily understandable. You can freeze this wave in either space or time. Let's say I freeze this wave in space. That amounts to, if you're looking at a water wave, freezing a wave in space means looking at a wave between two tall buildings, like a built-up ocean resort or something. Then you will have only the wave changing in time. So I'll be looking at something like this. Okay, here's time coordinate, and this wave is now only a function of y, is only a function of t. The other thing I can do is I can freeze the wave in time. How do you do that? You take a photograph. You go up in the helicopter and take the photograph of the ocean. Well, then you're freezing the wave in x, and you're getting a picture of the ocean. So that's what you're going to look at there. You're going to get distinctly different things from each of these graphs. From the graph that's frozen in space, you're going to get the period, because you're going to see the ocean go up and down at regular intervals, and that gives you a period of oscillation. You're still going to get the same amplitude, the y naught, from both pictures. So I drew them out of scale, but you're going to get the same y naught in both pictures. If you look at the wave, photograph of the wave in space, well, then you're going to be seeing this quantity called lambda, or wavelength. That's how you find out, oh, is there a tsunami, or is there just a big wave out in the ocean? Okay, so that's how you find the two different things by freezing two different variables. Now, once you have the lambda from a wave, you can get what's called the wave number, which is 2 pi divided by lambda. And once you have the period t, you can get what's called the omega, or the angular frequency of oscillation of the wave, which is just 2 pi by t. So I've told you how to determine both of these, and the relationship between the two is that the speed v equals frequency times the wavelength, where frequency f is defined as 1 over time. That's the relationship. And now if you look at f, which is 1 over time, I can write f as omega over 2 pi, and lambda as 2 pi over k. The 2 pi's will cancel out, and I get the speed equals omega over k. So that's the relationship between this way of writing the wave equation and this way of writing the wave equation. Well, once you have that, you similarly have b of x comma t equals b naught cosine kx minus omega t plus phi. The phase factor phi is not very important right now, but later on in optics, the phase factor phi is everything. So once you have these two, you put it in the wave equation that's satisfied for the E and the B wave. So here I can replace y of x comma t with E of x comma t, and I'll get the same thing, and B of x comma t, I'll get this to be satisfied. And the speed v turns out to be equal to 1 over the square root of epsilon naught mu naught. If you evaluate this, and I show you in my notes that I do that, then it turns out to be the speed of light. You can imagine how excited Maxwell would have been when he substituted these things in the wave equation and found the speed of light to come out. He basically had proved by that point that light is an electromagnetic wave. So it's a long and complicated story, but this is the result. And so now you can find t-shirts. If you go to websites that sell various kinds of t-shirts, you can find t-shirts that write these 4 equations, and it says something like nature said this, or Maxwell said this, and then 3 dots, and then there was light, which indeed is the case, because these 4 equations inevitably lead to the fact that you're going to get waves which travel at the speed of light. By the way, when I say there was light, it means anything, any electromagnetic wave. The electromagnetic wave spectrum is huge. You can have gamma rays from gamma ray bursters, which are violently emitting stars. You can have X-rays from black holes colliding or neutron stars colliding. I'm describing the natural things that occur in nature, not man-made things. Then you can have microwaves and from the cosmic microwave background in the ancient universe. And finally, the most boring thing is regular light that you and I use to just get around in the world.